is defined. And in fact, I think you could probably find a matrix here that would provide a clockwise rotation, but we've just defined it as anti-clockwise. And that's the one I'd expect to use. I think it's on the formula sheet, so I'd just stick with that one. So if you wanted to do a reflection over the line y equals mx, again, there is a proof of this, quite a nice proof in your textbook, which you can have a play with, but it relies again on some of the trig stuff that we'll do early next term. So I'm not going to go into that, but what I will say is this. We've got a note tan theta, tan inverse of y over x equals theta. So if you were reflecting over this line here, we wanted to reflect over this line y, oh actually it's got to be y equals mx, doesn't it? So it goes to the origin, y equals mx. You'll note here that if I draw this shape for a given point, this point here, which is x comma y, it could be somewhere on the line, and I recognise that that angle is theta, y equals mx has an interesting relationship between theta and m, and that is that m, our gradient, is equal to y over x because it's equal to rise over run. And this only works if there's no c value, by the way. It has to be y equals mx, not mx plus c. Then we have a slight variation. But also that tan theta is equal to y over x. And so therefore, m is equal to tan theta. M is always equal to the gradient, m is the gradient, so it's always equal to tan of the angle of elevation from the horizontal axis. So we have a relationship between our gradient and theta, just here. So that theta, any line will be defined by a theta, which will be the angle of elevation from the horizontal axis. And so the steeper the line, the larger theta is. And we can determine that theta by doing, and also therefore, theta is equal to tan inverse of y over x to determine that theta. So whilst we're reflecting over the line y equals mx, we're also reflecting over a line that has a certain angle of elevation. And it's that angle of elevation that provides us a way of doing a proof. And in fact, our reflection, as it turns out, can be done by this. Again, have a look at the proof, or have a look at the proof next term, or perhaps we'll go back and look at the proof next term. But that, where we now have, instead of, it's pretty much the same as we had for the rotation, except not, because the negative has moved from here down to the bottom one. But otherwise, it's just cos, sine, cos, this time of the angle 2 theta, and the negatives moved. And that will provide you that situation. And if we think about it, we want to move this point here, the theta, and then the theta provide us that kind of reflective property. It's not quite theta because that point might not have an angle theta here, but the idea is there. So we've got a theta here, we flip that theta over, it creates an angle of 2 theta. Go and have a look at the proof and you'll see kind of how that works. Yeah.
If you had a C value, would you just subtract that from all of your values?
Yeah, and that's probably a little bit beyond what you'll need to be able to do, but that's a good point. You could, if you had a C value, you want to reflect over that line, you could drop the C value from your coordinate, reflect over the line of y equals mx without the C, and then put the C value back on. That would work, yeah. And again, so obviously if it's just a coordinate, usually it's pretty trivial. If it's a shape with 3, 4, 5 vertices, then it's easier to use the matrices. But if it's if we get to functions, if it's a function, so if you wanted to reflect the function y equals x cubed minus 7 over the line y equals 2x, you could do that using this transformation.
Could you reflect trigonometric functions?
Yep. Using trigonometry. I mean, keep in mind that once you've defined that you're reflecting over the line y equals 7x, you know theta, which means that this is not a variable matrix anymore, it's just a bunch of numbers. They're going to be complex and not nice numbers, but they're just going to be a bunch of numbers. Okay. So my question now is, by what matrix would you multiply point 2, 3 in order to reflect the point across the line y equals 3x? Is it the same rule for y equals negative 3x? And also we might just confirm that it works as well. And to confirm that it works, the first thing I might do is sketch that point. Y equals 3x is quite steep. and 2 comma 3 is out here. 2, or y equals 3x will be go through 1 comma 3. So 2 comma 3, what's that? That's 1 comma 3. 2 comma 3 will be there. So let's say that's 2 comma 3. Can we see what that would reflect to?
You know, is it going to become comma? I'm going to get just 2 points and we have to work out theta.
It's going to go to the shortest point. So it'll go to this point here that makes a right angle and then do the same distance over and end up somewhere here. And my diagram's not to scale. It's not perfect, but it's not bad. So somewhere here, it might be 0, it won't be 0.3 because it's going to move up. It might be 0.4, but I suspect we're going to get a less than nice number. And I suspect it will be somewhere in this vicinity, so maybe at 0.5 comma something. But we'll see. We'll see. We don't know this point of reflection, and we have enough information. We could certainly work it out, but it's going to be pretty hands-on to do that. So let's do it the other way instead. If we've got this, we know that that coordinate is 1 comma 3. We could work out theta. But we don't really need to work out theta because we know that m equals y over x, and therefore theta equals tan inverse of y over x, which is just tan inverse of m. So all you have to do is tan inverse of the gradient. It will give you the angle of elevation. In this case, that's tan inverse of 3. And what's tan inverse of 3? So? Do you know what it is? On top of your head? Yeah. 1.25. Thanks, Chris. Can you keep that value on your calculator for me? Is that it sounds like it's in radians to me.
71.57.
1.57.
71.5.
Oh, you've given it to me in degrees. I'm going to go with radians. Let's stick with radians.
Why?
Why radians?
Why not? And the reflectional matrix will be equal to cos of 2 theta, sine of 2 theta, sine of 2 theta, negative cos of 2 theta. And in this case, what's that going to be equal to? Cos of approximately 2.5, but I'd like you to do this if you can, Chris, with that value. You could do it Harvey as well, but with the, you'll have 75, but 150 odd. Sine of 2.5, sine of 2.5, negative cos of 2.5, and that matrix is what?
First one is negative 0.52.
That's cos 2 theta.
Yeah.
0.52.
Negative.
6 theta because it's y equals 3x.
Dude, what's that?
Wouldn't you have to change it because it's y equals 3x, not just y equals x?
Change it in how? In what respect?
It's not just cos 2 theta.
Well, that's the rule for reflecting over the line y equals mx. You just have to work out the gradient based on m, which we've done with the tan inverse of m.
The sine one is 1.14.
1.11.
1.14. And then it's negative 1.1.
I'm a bit worried about the cos one.
Yeah, because that's really close to what I've got.
Should be in the second quadrant. Should be negative. I feel like it should be negative.
The negative cos is 0.52.
Oh, so negative cos is 0.52. So is positive cos negative 0.52?
Negative, yeah.
Yeah, okay, cool. That makes more sense. So we get that matrix, and therefore our coordinate, which I'll call P dash, is equal to that matrix, negative 0.52, 1.14, 1.14, 0.52, times by the coordinate, which is 2, 3. And for me, I get that that's approximately equal to negative 1.04. And then 3 of those is 3.14, 3.42, 2.38, and then 2.28 plus 1.56 is 3.28, 3.78, 3.84, which doesn't make sense either, because now the point's over here somewhere.
Yay! Good job.
It's all right.
degrees.
Give me the calculator. Where's my calculator gone? Oh, it's here. Don't worry. It's fine. Got it. So?
I just feel like you have to change it because of the gradient. Does that mean it's always 2 theta no matter what the gradient is?
What the gradient is? Yeah, it's always 2 theta, and you get a different gradient means you get a different theta. Each gradient has a different theta value.
Oh, yeah.
Shift tan of 3 is that. Okay. I'm going to set up a matrix E with that. 2 by 2, it's going to be cos of 2 times my answer, close brackets, sine of 2 times my answer. You've taken me down this path. Sine of 2 times my answer, and then negative cos of 2 times my answer. I get negative 0.8 and 0.6, 0.6. Well, I've just done it in radians, and that's what I got in radians.
What?
Well, you should get the same thing because we're just transforming the radians and then doing trig again back out.
It's actually 0.59. Oh my goodness, Chris. I didn't know. Yes.
And then when I multiply that by 2, 3, I get 0.2, 3.6, and 0.2, 3.6 is about there. Which is what I expected. Nice. Not super nice, but nice. Yep, we could confirm with Desmos. You're right. Let's do that. Because we can. So was it y equals 3x? And 2, 3 and 0.2, 3.6. How does that look for a reflection across? Now, if we found the line that connects those 2 points, it should form a right angle with the line y equals 3x, and we can confirm that by checking the gradient. In fact, the gradient should be y equals 3x has a gradient of 3, it should have a gradient of 1/3. So it should be y equals 1/3 x, and then it's going to be, no, not 1/3, sorry, negative 1/3. And then it's going to go up to not a bit higher than 3.6. Oh, it's going to be annoying, isn't it? Whoa, x3. Yeah, back 0.2. Up 1/3 of 0.2, 3.66666666. And that should be right angles, and it does, it works. There we go. Okay, cool. So there we go, reflection across the line using that matrix E, and I'm sorry that I can't go into a lot of detail about y, but the y is here. It's interesting, it involves a bit of circle theorems, a bit of isosceles triangles, and some trig stuff we haven't done until next term. So do have a look at that. And otherwise, I'm going to leave you be for a little while. Can I just make a note, though, that I didn't do projections? So have a read of that. I don't think it's that hard. And I can talk about that a little bit later if need be.